Hey guys, previous lecture, I mentioned the end of a ring, and the armature reaction. I said more deeply I will explain, right? So today we will learn about overheating of the iron core end of a generator stator part and the armature reaction. You know what I mean? Depending on the load, RLC's, load. So first of all, as I mentioned here, overleading the end of the stator iron core, we say retaining ring. You know what I mean? Retaining ring is here, these two part, right? And then, so, uh, okay, I will, yeah, I'll explain to here. Uh, yeah, it's better to here. So first of all, retaining ring is here, right? So in the rotor, there's cores, inserted, right? So, but the end of part, we need to also, protect them, when the rotating is, so fast, right? So if we didn't, cover it, it's you know, going out, you know what I mean? Pull away. So we had to, install the retaining here, as you guys see cover, right? But so I want to explain you guys first. Look at that. So first of all, as you guys know, here we have a DC voltage, right? And then here IF, exciting current, right? And this is rotor. And second part is here. Uh, here is stator, and then here is depending on the load. So IL, yeah, load is here. And then IF make pi F make EF, and then EF make EF, right? Pi F make EF, right? Induce the voltage. But depending on the I, it make it also I pi 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 load. I say pi A. So which means pi, it's make it U1 pi net equal pi EF pi F, what I mean EF, right? And then I'm showing is that plus pi A. Yeah, you know what I mean? Actually, this is the same, right? So I'm saying pi F here. I net equal. So what I wanna say is that this is, our general situation is over exciting. You know what I mean? It's a supply. No, what I mean is it's a we are consuming. You know what I mean? And which means that we are supplying the reactive powers, right? So the result is here in the retaining. It's a over exciting situation, general situation. It's already saturated. You know what I mean? Saturated means like for example, mm, I wanna say is here. There's two circuits. It's a resistor, both of them, okay? And current is here. Here's a 1 ohm. Here's a 10 ohm. So current is mostly wanna go to here, right? Because it's there's a low resistor, right? So which means if it's a retaining means is generally saturated, which means here is too much ohms. You know what I mean? So that's why the fluxes. This is in case flux, right? Yes, N S, right? Sorry, N N S, because going out here, right? coming out from here. In, out, right? NS, now. So what I meant is retaining is generally saturated, which means lots of resistance. You know what I mean? It's the same concept. You know what I mean? So if it's not saturated under exciting situation, which means retaining ring is like a low resistor. You know what I mean? It's the same concept. So in this case, our general situation, retaining is saturated, which means the flux doesn't want to go to this way. You know what I mean? This way. They want to go to this way. You know what I mean? Vertically. You know what I mean? But as you guys know, here, the stator is, you know, laminated like this. It's a thin, you know, plate, and we accumulate, right? For, you know, reduce the eddy current. I already made the eddy current, right? So eddy current is gonna be like this. But since we laminate, eddy current is small. But the matter is, you know, in under exciting situation, retaining is not saturated. You know what I mean? So because of that, leakage fluxes, you know what I mean? It's gotta be like this way. You know what I mean? So which means is perpendicular. You know what I mean? Axial here, this way. It's gotta be go to this way. You know what I mean? So make the eddy current is gotta be more bigger. Here, plate is really big here, this side, right? So that's the problem. You know what I mean? That's the result. What I meant is, I will say again, retaining our general situation is overexciting, right? We are consuming reactive power, and we are supplying the reactive power, right? At this time, it's saturated. That's why the leakage flux is small. So we could like neglect, you know what I mean? But in the under, you know, exciting situation, like at late night, you know what I mean? Like when we are sleeping, we don't need too much powers, you know what I mean, generally. And that time they need to observe, because our line, there's lots of reactive powers. So we need to observe it. If we didn't, penalty effect happened, right? Yeah. So what I meant is, if you guys understand what I, you know, what I teach you guys, and I'm learning, you know, while I'm preparing this, so we can understand easily, right? Yeah, that is a result. So yeah, in under exciting situation, the retaining is not saturated. That's why lots of leakages, you know, fluxes, it's causes. So make it eddy current is here, this plate. You know what I mean? Perpendicular way. You know what I mean? It causes eddy current. You know what I mean? That's a problem. Yeah. Actually, easy, right? If you guys understand. And the other part is here. Armature reaction, right? I said the armature reaction is depending on the load, right? So first of all, we made it, oh yeah, here. As I will try to draw again this. Look at the guys. So first of all, we need to make it this drawing, right? Equivalent to circuit. And then we need to draw the page, right? But in this case is under exciting, under. Previous lecture, we did over exciting, right? Our general situation. So which means now the current is leading, you know what I mean? Leading. So I will draw this, guys. So first of all, we made the voltage equation here 1 and here 2, right? I hope so. This is working. So first of all, we need to make it here. The reference point is V, right? V, V0. Our current is now lagging, right? Yeah. No, leading, sorry guys. Yeah, leading, right? So here, R and X, it's the lines resistor and the leakage reactance, right? Yeah. So it's an in phase here, right? INI, but it's a small. Look at that. Yeah, small in phase, same. But here, 90 degrees different because of J, right? So from here, 90 degrees is here. So color I should change. Okay. Here. Right. So R is more smaller than JX. You know what I mean? So we make it at this is E net we made it, right? So E net is here. Here is E net. And then we need to one more time, right? JX. But IA, you can see IA's direction is here, same, right? JX, 90 degrees, same, right? But I said the magnitude is 90%, and this is 1%, or 90.90%. You know what I mean? Like almost it's better. So we could neglect. You know what I mean? Actually, we cannot neglect. But what I mean is, it's a more simply equivalent circuit. You know what I mean? So I make it with this this one. So yeah, and then this is gonna be our EF. You know what I mean? So after then, we need to make it one more thing. So pi net, yeah, pi net equal pi f plus pi armature, right? But look at that. In this case is here. E net is here, right? So E net is a 90 degrees degree here, and then and EF is sorry, EF is here. Here. It's too small, sorry. Where is the image? Yeah, I'll make it more clear. Yeah. So 90 degrees here, right? And this, yep. Which color is that? 90 here. And here, yeah. And then I is the same here, I, right? I, here. This is what we draw. You know what I mean? So let's see here first. So what I did is here. More clearly, I will explain one more time. Here, we need the reference point, right? V equal 0, right? So I is this time is leading, right? I. But R and JX is small number, right? But R is in page. That's why I put here. And 90 degrees because of JX, right? And then ENET is, so we make it this ENET, right? Here. And then we also need to, here's IA. IA is the same, right? But we need to JXA. This is 90 degrees same, right? But the value is more magnitude. Magnitude is more bigger, right? That's why I wrote down here, drawn more longer, right? And now EF. And EF is 90 degrees. Here, pi F, right? Pi F. And then here, E net 9 degrees here, right? So in this case, is the result is, look at that, E net compare and here E pi f. What happened here? Pi net's gotta be more bigger, right? Pi net's gotta be add and then more bigger, right? So we say now it's increase, right? It's a different, right? In capacitive, inductor, no, capacitive load, or what I mean is leading current, the pi net is increase, but inductive case, decrease. And then in pure R load, generally we don't have nowadays a pure R, you know what I mean? But in pure R situation, it's the same, but that is a kind of, yeah, I will show you. I will explain about this. Yeah. So first of all, I will explain plus the pure R situation. So what I mean is here, our generator, right? So as you guys can see here, the flux N, S, right? The current is here, right? So the current gotta be at first time, it gotta be here and here, right? But Lenz's law, because of the coil, it's inertia, as we know, right? Because of that, inertia's phenomenon, actually, reaction, armature reactions happen. So our flux, if it's here, it gotta be here. So, but it disappeared. What I mean is, but because of that, the current is changed. You know what I mean? So in this case, the first picture here is 1, and this is 2nd, and this is 3rd. And in first situation, current is this way, right? As I draw this way, right? But we'll look at it here. What happened? So because of the armature reaction, it's rotating the second part here, from here, right? But current is the same. But what I mean is, if it's here, the armature reaction gotta be here, right? So that's why the current is totally reverse way. That's why now we're focusing on this because of the inertia, and the armature reactions happen. So look at that, guys. Next picture. So I'm saying is now pure resistor, okay? So what I mean is here's, this dot, it means, it's coming out, like, for example, from the monitor to come out to me. And this X means it's inside from me to the in the monitor. You know what I mean? So what I want to say is here, look at that. So here's fluxes coming out, right? From N, and they're coming to inside L, S, right? But we're focusing on these two parts, A and A dot here. So I said the dot is coming out, right? Coming out. So if it's coming out, fluxes, so for example, it's coming out, look at my hand. The current is same way, right? Like if it's coming out to me, current, look at my way, my hand here. So that's why the current is here, right? The fluxes, what I mean is. And then for here, look at that. It's inside, right? That's weird. Inside, right? The current is this way, right? If it's going to X, you know what I mean? So what I mean is here. Here's, you can see this purple color. The rotation is totally different. One is this way, and one is the other way. So what I wanna say is it's pi f also. Here's, we made it, right? but because of the this dot, you know what I mean? So look at that. I will try to do separate here. Separate. So one part here, look at that. It's plus plus, right? Same way. But one part is here, we say plus, and here is 0, right? Minus, right? But look at it here, what happened? Here is also 0. And here is the same way, right? So plus. What happened? In pure resistor, you know, we say this is a quadrature reactance or cross magnetization, you know what I mean? So in actually in pure R inductive, it's nothing happened, you know what I mean? Because as you guys can see, this is the result. Yeah, it's kind of difficult, right? But I hope so you guys can understand. And the second part is here, inductive load and the capacitive load. I will explain. So what I want to say is, look at that. First of all, we have a plus and minus, right? And here's IF, right? And then here's rotor, and then we make it pi f, right? And here we make it EF, right? EF is actually pi f, right? And here's if we add the load, right? So current is if its current is IA, IA make here also pi a. So pi net, I would say pi net equal pi f plus pi a, right? So I will say is this pi a is depending on the load, right? So I'll try to explain, guys. First, get that. So try to understand. It's a reference point to pi f, IF, exciting current is here, right? Here's IF 0. And then second part is it make it the fluxes, you know, make it, I would say also flux, flux F. It make it induce this EF, right? EF, EF. So here's 90-degree differences. So EF, right? But if it's inductive, inductive means lagging, right? From here, the lagging current is happened 90 degrees voltage, right? Here's IA and pi f. No, pi a, right? So which means the result is IF, right? Pi f plus armature, you know, reactions flux is here. Look at that here, and then pi f is 1A zeros different. That's why it gotta be more smaller, decrease. You know what I mean? But look at that. In this case, in capacitive, look at the same. We start the IF here, right? IF, and here's a 0. And also it gotta be pi f, right? It induces the EF here, right? EF induced. But in capacitive load, it's a leading current, right? Reference is now from here, it gotta be leading. Leading means 90 degrees more faster, right? Precede. So look at the here. Same. So which means here's IA or IF, pi A, right? What happened this time? Pi F, pi F plus pi A is the same way. You know what I mean? So it gotta be increased, right? You guys understand, right? If you guys have a confusion, just let me know. I'll try to explain, more deeply, more easily, you know what I mean. But the differences is here. in pure resistor load, yeah, if we separate two parts, left side and the right side, right? And quadrature reactions or cross magnetizations happened. So one part increase, one part is zero. And the other part, the underside is one part is minus, one part is plus, right? So nothing happened. Yeah, today's lecture is kind of complex, but if we understand the mechanism, it's easy, to understand. Yeah, today's lecture is done, guys. Thank you.